Today we want to look at the Navier-Stokes equation and prove its global well-posedness in the two-dimensional case. So let's look at what local theory gives us. Here we have written the Navier-Stokes equation in its mild form or in the Duhamel formulation. And the local theory gives us unique maximal solution in HS, as long as S is strictly bigger than n over 2. The theorem comes with a criterion on global existence of solutions. If the maximal time of existence is finite, then the HS norm of the solution goes to infinity as t goes to capital T. So in order to show that capital T is equal to infinity, what we need to do is we need to show that this norm does not blow up. Show that we have some estimate on the HS norm of U depending on time, and this capital F never becomes infinity. It can go to infinity as t goes to infinity, but it doesn't go to infinity for any finite time t. These kind of estimates are called a priori estimates, and usually in order to derive the a priori estimates, we simply assume that we have a smooth solution. And before deriving these a priori estimates, let's look at regularity properties of the local solution. So we write the mild formulation in this way, where U0 is the linear propagator, and W is given by the nonlinearity of the equation, and N is the integral mapping here. So we know that U0 is continuous and it becomes smooth immediately after an infinitesimal amount of time. So it will be in H sigma for any sigma as long as the time is positive. So note that we have this open interval. We don't include t equal to 0 because at t equal to 0 this is equal to g, and g can have finite regularity. We want to show that the solution is actually smooth in space for any fixed time t between 0 and capital T. And for that we use the smoothing property of this heat propagator. We know that the solution is in CHS, then the product will be in HS, and when you take the divergence it will be in HS minus 1. So this W variable is in CHS minus 1. And by the smoothing property of this integral operator, NW will be in H sigma for all sigma strictly bigger than S plus 1. So we can almost raise the regularity by 2. Now, because NW is in H sigma, you have U in H sigma. So note that we started with HS and we ended up with H sigma. So that means we can actually repeat this process. For example, we say we get W in H sigma for all sigma smaller than S plus 1. Then you apply the integral operator to get that NW is in H sigma for all sigma strictly smaller than S plus 2, and so on. We can show that U is actually smooth in space. It is in Sobolev space H sigma for any sigma. Now we will look at the temporal regularity, what happens to the regularity in time. The U0 part satisfies the homogeneous heat equation, so the time derivative of that in the strong sense is equal to the Laplacian applied to U0. In order to differentiate the solution U, we need to differentiate the integral part here, the inhomogeneous part. So we can write this difference in this way. First, we take the integral from t to t plus h, and the second part here is the integral from 0 to t. So this should be actually t. So the second part is the integral from 0 to t, and we actually replaced the difference between these two terms by the time derivative of this term multiplied by h with error small oh. And then we replace the time derivative by the Laplacian of that term, because it's the linear heat propagator. So that's why we have this Laplacian term here. Let's call this term v tau, and then we can write the second term as the integral over the Laplacian of v tau. And over here, by using the fact that h is small, we can replace this term, the term at tau equal to t plus h. So in that case, this term will become identity, so that you have wt and then multiplied by the length of the interval h. And this will give us another small oh error. And that means if you take the time derivative, so we will divide by h here and h here, we will get first the time derivative of u0, that is here, then the time derivative of the integral term, which will give us w and this integral here. Now at this point, we use the fact that v has arbitrary smoothness in space. The Laplacian of v will be a continuous function in any soluble space Hs, and the Laplacian acting continuously between Hs plus 1 and Hs, we can bring Laplacian outside of the integral. And if you look at these two terms here, this is exactly the definition of u. So that is Laplacian u plus w. And w was the nonlinearity. In addition, we have w continuous and Laplacian of u continuous. That means the time derivative is continuous, so it is C1. And it shows that our mild solution is actually a strong solution. Now we want to look at higher regularity. In order to do that, basically we look at this equation and try to take the time derivative. And the main trouble here is the nonlinear term w. So let's look at the nonlinear term. The main nonlinearity is, of course, this u squared nonlinearity. And if you write this difference by using the fact that it's a bilinear operation, we're going to get sum and difference. Taking a finite difference on both sides of the strong solution formula, we get difference between the time derivatives on the left side, and on the right hand side you have the difference between the Laplacians, and we get this term, the ray projector divergence applied to this bilinear term. And if you take the limit h going to 0, you see that this becomes 2u, and that will become the derivative, so that you get this equation for the second derivative of u. Since the right hand side is continuous, the left hand side is continuous, so the solution is in C2 in time. And so on, we can show that, for example, the solution is in C3 and so on. We get C infinity in time for all h sigma. And we can now easily turn everything into space-time regularity. So first of all, since u is continuous in time with values in h sigma, taking sigma, for example, strictly bigger than n over 2, that will show that it is continuous in time with values in the bounded continuous functions. And that will immediately imply that u is actually continuous as a space-time function. Then we look at the time derivative here. We know that this time derivative exists in all h sigma, in particular when sigma is bigger than n over 2. That means this limit exists as a uniform limit in space. That means the time derivatives exist in the classical sense. And so on, we can show that the function is actually C infinity in both space and time. And that actually shows that our mild solution is a classical solution. Note that all these are possible only because of the heat kernel that has this smoothing property. If it was a hyperbolic equation, this would not be true in general. Now we consider how to get a priori estimates. So what do we need? We need to have a control on the HS norm for S strictly bigger than n over 2. We may show that HS norm is conserved, bounded, or HS norm is bounded by some function of time. Any of this will be enough to show that we have a global existence. Thinking of integer S, when n equal to 2, for example, n over 2 is 1, so s must be 2. When n equal to 3, this will be 3 over 2. So showing that H2 norm is controlled will be enough in 2 and 3 dimensions. So let's try to focus on the H2 norm. It all starts with this basic energy estimate. So let's write our equation. And we multiply by UK and integrate. So UK is the kth component of our equation. So if you integrate, first here, this is equal to half the time derivative of the L2 norm of UK. We are actually summing over k here. The second one here, by integration by parts, we get minus the H1 semi-norm squared. The boundary term will vanish because UK are in all subtle spaces. Now we claim that this is 0, that we will show shortly. Over here, we can do integration by parts to show that this is P times divergence of U, and the divergence of U is 0, so that term is also 0. The boundary terms vanish again because of the decay of U. Now for this trilinear term, we write it in two ways. First, use integration by parts to write it's equal to minus this integral. Second, we simply use the product rule to take the derivative of this product. So you get here divergence of U. Because divergence of U is 0, that is 0. And over here you are taking the derivative of UK. And if you look at the left and right hand side, this is exactly same as that term, which means this term is equal to 0. So that's why this term, trilinear form, is equal to 0. And collecting everything, that now shows that the time derivative of the L2 norm squared plus the H1 norm, H1 semi-norm squared is equal to 0. This is called the basic energy identity of the Navier-Stokes equation. If you integrate this, we will get the energy, that's just L2 norm squared or half in front, plus the integrated H1 semi-norm squared is equal to the initial energy. This is also called the basic energy identity or energy estimate, because all of these terms on the left are positive, and it's going to give us, for example, E, the energy is bounded by the energy at the initial time. This estimate is usually written in this way. U is in L infinity L2 and L2 H1, because it's H1 norm squared integrated in time here. And we introduce this notation, the initial energy will be called E0. This gives us L2 norm bounded and H1 norm square integrable, but we need H2 norm controlled. So let's go higher and try to estimate H1 norm. In order to do that, we look at our equation and take one space derivative. So this can be thought of as one particular space derivative along one direction, or it can be thought of as collection of all the first derivatives. Then we get this equation for the first derivative, multiply that by the first derivative and integrate. If you do this, similarly to before, we get time derivative of the L2 norm of the first derivative. Over here we get some type of dissipation term again, and we get this trilinear form. Now this trilinear form is not going to be 0 for these higher estimates. So this is 0 only for the basic estimate, and this gives us the main trouble in the estimates. So let's try to estimate this trilinear form. First, let's just take U out, estimated by the L infinity norm of U. Then the other term will be estimated by L1, and then use Cauchy-Schwarz to estimate this L1 norm by the L2 norm of the second derivative and L2 norm of the gradient. At this point we use this inequality, which says that AB is smaller than epsilon A squared plus C epsilon B squared. Here epsilon is a positive number that can be chosen arbitrarily. We choose this epsilon to be small, and C epsilon is some constant depending on epsilon. So we want to single this term out, the second derivative term, so that will be multiplied by some small constant, and the rest is the L2 norm of the gradient and HS norm of U. The reason why we choose epsilon small here is because there is this minus second derivative term, And if you choose epsilon small enough, you can hide that term under this negative term. So in the end, let's say, for example, we choose epsilon equal to half, then we're going to get half extra of that second order term. So putting that second order term on the left hand side, we get this. Similarly to the basic energy identity, but in this case we really have an inequality. We get H1 energy, let's say, and then you have this second order term which can be called H1 dissipation, is bounded by Hs norm squared times the gradient. For the moment, forget about that term. It says that the time derivative of this H1 semi-norm squared is smaller than Hs norm squared times H1 semi-norm squared. So this is something that we want to bound. And for this, we can use a differential inequality called Grunwald's inequality. This inequality says that the time derivative of some quantity is smaller than some function times the quantity itself. Then we get this exponential bound, where the right-hand side is the quantity at time 0 and integral of the coefficient. So we see that in order to have good bound, what we need to have this coefficient integrable. It does not need to be bounded. What is coefficient in our case? The coefficient is the Hs norm squared. So we need to have this to be integrable. In the Grunwald's lemma, proof is not very hard. Sufficient condition is that the coefficient is continuous and the quantity itself is differentiable in time. So applying the Grunwald's inequality, we get this bound. Now you have the H1 semi-norm squared here. That's the initial value of that term. And we have this exponential term in which we have integral of the Hs norm squared. We say that this estimate turns L2Hs estimate into L infinity H1 estimate. So we only need square integrable Hs norm. That would give us bounded H1 norm. So that means we need L2Hs control, and S should be strictly bigger than n over 2. For two-dimensional case, S should be strictly bigger than 1, and three-dimensional case, S should be strictly bigger than 3 over 2. But what we have is L2H1 control. And you can see that in 2 dimension there is arbitrary small gap between what we have and what is needed. But in 3 dimension there is finite gap. It is 1 over 2 between what is needed and what we have. The 3-dimensional case is not solved, but in 2-dimensional case it is possible actually to show global existence by using a slightly different approach. So in 2-dimensional case, the successful approach is now, this is our bilinear term. We use a slightly different bound. First we group in this way and use Cauchy-Schwarz to bound it. Then we use Holder inequality to bound u times nabla u. So you get L4 norm of u, L4 norm of the gradient of u, and L2 norm of the second derivative of u. At this point, we use the so-called Ladyzhenskaya inequality. This inequality works only in 2-dimensional case. It says that L4 norm of a function is bounded by L2 norm square root of the L2 norm of the function times the square root of the L2 norm of the gradient of that function. Now by using this inequality for both L4 norms, we get square root of the L2 norm and full L2 norm of the gradient. Then you have L2 norm of the second derivative raised to the power 3 over 2. That's because half power coming from the application of the Ladyzhenskaya inequality to the gradient, L4 norm of the gradient. At this point we use this elementary inequality where P equal to 4 over 3 and Q equal to 4. Here we have square of the L2 norm and fourth power of the L2 norm of the gradient. So let's look at this. So we start with this equality and we have bound on the trilinear part, so that we get this term here on the left hand side, the time derivative of the H1 energy plus H1 dissipation term. We have H1 norm squared times h1 norm squared. For now, we forget that term. In the ground wall inequality, we think of this term as being bounded, and we think of that part as the multiplier a in the ground wall inequality, so that we need to have integrability of this product, which we have actually, because this is bounded in time and this is integrable in time. So that gives us h1 bound. So by applying the ground wall inequality, we have h1 energy, the initial value of that energy, and exponential of this integral. Over here we can say this is bounded by the initial energy, that is E0, and this integral is bounded by also E0, so it becomes E0 squared, and call that the initial h1 energy E1. Then we can have this quantitative expression. So that gives us L infinity h1 control. Then we can now turn this into L2 h2 control. Look at this estimate here. By integrating this estimate, we will get integral of that second order term, and from here we will get E1 at time t minus E1 at time 0, and putting the E1 at time 0 on the right hand side, we will get this estimate. The integral of the second order energy is bounded by the initial value of the first order energy and this integral, and substituting the values, for example, this term is bounded by that, and so on, we can get this quantitative bound. In particular, we get now linear in time estimate in L2 H2 norm. We need actually L infinity H2 control, not L2 H2 control. So we need to go one order higher. We repeat the procedure. We start with the equation, take second derivative from the equation. So this can be thought of as generic second derivative or collection of all second derivatives, and multiply it by the second derivative of u and integrate. So we get time derivative of the second order energy on the left side, and over here dissipation of the second order energy and some trilinear term. So at this point, bounding the trilinear form becomes easier because we have many derivatives here. First, here we're going to use one integration by parts. So take one of these derivatives over to the other side and use Cauchy-Schwarz. So we get third order derivative here, and we know that this can be written as divergence of u cross u, and there is one derivative left here. So together with that one derivative, you have here h2 norm of u cross u, and because h2 in 2 and 3 dimensions is an algebra, this norm can be bounded by h2 norm of u squared. Then we use our inequality to have epsilon times the third order norm plus some constant times h2 norm to the power 4, and we write h2 norm of the power 4 in this way. So we can see that this third order term can be absorbed by that minus the third order term, and over here we treat this as a coefficient that will give us bound on the h2 norm. So the h2 energy is bounded by the initial value of the h2 energy times the exponential of the integral of the h2 energy squared, and we know that h2 energy is squared is actually integrable from the previous step on the h1 energy estimates. And putting these quantitative constants, we actually get this. I think it should be h1 there. So it's an exponential bound, exponentially in time. This shows that h2 energy does not blow up in any finite time. That means the two-dimensional Navier-Stokes is globally well posed. Now here we assume that the h2 norm of the initial data is bounded, but if h2 norm is not bounded, what we can do is, because we have a local existence, we evolve the equation for infinitesimally small amount of time, and then the solution will become infinitely smooth. Then we can start this argument at that point So the theorem actually works for any initial data as long as the local existence theorem is true. What is left is, of course, this Ladyzhenskaya inequality. Now let's prove this Ladyzhenskaya inequality. Here we have actually explicit constant. We want to prove the inequality for all test functions, which will make it true for general H1 functions by density. Let's say this is the support of our function f, or u in the proof. Then we can write the u squared as an integral from minus infinity to x of uu 2 times ux, because 2 times ux is the x derivative of u squared. Similarly, we can write it as integral over y of y from minus infinity to y. So that means taking maximum over x on the left side here, for fixed y, maximum of u squared is smaller than 2 times the L1 norm of ux over x with fixed y. Similarly, maximum over y with fixed x is bounded by this integral over y with fixed x. So these two formulas are here, and we immediately start bounding the L4 norm. You write u4 as u squared times u squared, and first we maximize over x. So the outer integral is over y, and for any fixed y, maximize over x. In the inner integral, for any fixed x, we maximize over y. At this point, we use our inequalities. So we get 4 times ux integrated over x. Then you have integral over y. So that will give us this integral. Now over here, we get uuy integral over y first. That maximum is bounded by that integral. Then you have this integral over x. So that gives us this integral. So you get the product of two double integrals. Then we use Cauchy-Schwarz. So you get L2 norm of u and L2 norm of ux, L2 norm of u and L2 norm of uy. Then the product of ux and uy is bounded by half ux squared plus uy squared, and that gives us what we want.